Thank you. And thank you all for coming. So I'll be taking the use of small unmanned aircrafts to a slightly different field. In this talk, I'll be sharing with you a method that us as geologists, we found revolutionary in studying ancient Earth systems and their depositional processes. As the title suggests, we're using this methodology to study stratigraphic architecture of Miocene age thin-bedded turbidites exposed on the east coast of New Zealand. And before I move forward, I'd like to acknowledge all collaborators at GNS Science and the primary funding source for this work, Stanford Project on Deepwater Depositional Systems. So this methodology was largely motivated by a challenge that all field geologists face, and that is, in a general sense, the inaccessibility of rock outcrops. There are many outcrops that are difficult to view. For instance, this photo showing really extensive wave-cut platform off of the coast of New Zealand that is exposed at low tide, but difficult to view because of its low topography and relative flat-lying topography. So it can only really be viewed from above or from the air. There are also many outcrops that are virtually impossible to access or climb, as the case may be, such as these coastal cliffs in the lower right-hand corner. So the solution? An affordable small unmanned aircraft or consumer-grade drone. It's portable and very maneuverable in the air. One that has a built-in camera is essential, and it's a high-resolution camera. And one that can fly systematic flight patterns that can often be automated or pre-programmed as well in order to collect the imagery required. For this project, the UAS, or the drone that was used, is the consumer-grade DJI Phantom 2 Vision quadcopter, for those of you who are familiar. The data that's collected by this drone can then be implemented into photogrammetry software. It's quite easy to use, and it implements a methodology known as structure from motion, or SFM. And what results from this is high-resolution digital elevation models of the entire outcrop. And again, for this project, what we've used is Agisoft PhotoScan Pro. So again, as mentioned before, this methodology is being used on the North Island of New Zealand. Here's a geologic map of the North Island, highlighting the two locations where deep water deposits of Miocene age are being studied. These are the Middle Miocene Tunanui Formation and the Lower Miocene Whakataki Formation. These deep water deposits are recording deposition on or at the very base of slope in deep water depositional environments, which is roughly analogous to modern deposition out here in the current configuration of the East Coast Basin in New Zealand. In particular, the deep water deposits that we're interested in are thin-bedded turbidites, as mentioned before. The importance of studying these thin-bedded turbidites is to provide outcrop analogs. Thin-bedded turbidites represent a variety of sub-environments in deep water systems, and yet the detailed stratigraphic architecture of thin-bedded turbidites is actually poorly represented, mostly due to issues of resolution with large subsurface data sets. Thin beds cannot be imaged by seismic reflection methods or really well resolved with well-logged data, and individual beds can't be correlated with just conventional core. So the outcrop is really useful and offers really useful information. And yet, another importance of these thin-bedded turbidites is they can prove to be important hydrocarbon reservoirs as long as we understand their lateral geometries and if we know that those are laterally continuous. So to study these thin-bedded turbidites, we're interested in multiple scales of quantifying stratigraphic architecture. And this starts with centimeter scale of looking at very small structures and individual beds, and then stacking patterns of how thin beds stack one on top of one another. And then this scales upward to lateral geometries of kilometers and kilometers of available exposure that we have in New Zealand. General workflow to study these scales and address the questions that we're asking is first to make observations and measure stratigraphic sections in the field, then to fly the drone over the entire field area and collect imagery. Then we georeference the photos or document rather, ground control points, and then models can be built using structure from motion, or SFM. Then finally, the models and the field data can be combined for much better and further interpretations. So for those of you who are not familiar, structure from motion is an imaging technique that estimates 3D structures from 2D image sequences. It does this by using aerial images that are overlapping, slightly offset, and it uses those images to create and then enhance terrain data. So essentially, it creates in relative space referenced 3D point clouds or models that then can be ground truthed, aligned with ground control points, and georeferenced, creating this georeferenced high-resolution terrain map or model. So I'll walk you through the general workflow of structure from motion, and that starts with acquisition. So on the upper left-hand corner, we have a digital model of just a portion of one of those wave cut platforms, and we can see all of these thin beds are near vertically dipping, and here's a much thicker sand bed here. Each of these squares kind of floating in space above the model represents the estimated position of the drone at the time that a picture was taken. And so each of those boxes is essentially recording the position of the drone when that photo that was used in the model was taken. An example of one of those photos is that highlighted pink box towards the very far right of that image, and in the bottom right-hand corner, just to give you an idea of the imagery that comes out of the drone. You'll notice all of these near vertically dipping beds, and you'll notice that there is some fisheye distortion due to the fisheye lens. However, this does no effect on the model. This is rectified through the modeling, or the software process of creating the model. Here's another picture, this time from this location towards the top of this outcrop. And when dealing with hugely extensive outcrops, such as these wave-cut platforms where thin-bedded turbidites are really well exposed, the use of a drone can cover huge areas, which is really beneficial. Also, it can obviously fly at various elevations, which results in models of variable resolution. We can have models that show a really good overview of an outcrop that's great for mapping, or we can really get down to the nitty-gritty details and show details that are comparable to those that can actually be observed on the ground when working in the field. Here's another example of a model generated of a near vertical outcrop. So this is more of a cliff outcrop with, again, the photo highlighted towards the very bottom of the outcrop. Here's a photo highlighted towards the middle. You can see all of these thick sands here. And then towards the very top of the outcrop with actually a little white goat for scale that the camera captured. So this documentation of this cliff would not be possible without the use of the drone, given the vertical nature of the exposure. Now, after acquisition, selected input images taken from the drone, from whatever the drone is captured, are aligned and virtually stitched. A point cloud is created with key points that are identified or selected as invariant to image scaling and to rotation. So these are all the key points, creating just a sparse point cloud. You can barely kind of get to see a glimpse of the model that we just saw, but now being created in its early stages. Then, as I already hinted towards before, the camera positions from acquisition are estimated relative to one another. And then a wireframe of the 3D model is created. And this is to start incrementally estimating 3D scene geometry. And then finally, this allows for processing of increased point density, creating a dense point cloud. Then we can create a textured 3D surface, or DEM virtually. And then finally, we can drape the orthophoto that was derived from the structure from motion software over top of that DEM for a very photorealistic DEM. So to drive this point home, the digital elevation model that's created, just the filled in, can really be best viewed and then further interpreted, even in the comfort of your own office, once that imagery or orthophoto generated by structure from motion software is draped over top of it. If the images are tied to ground control points, then the final result is a fully georeferenced high-resolution photorealistic DEM. So in summary, I hope that I've been able to show you that the advances and huge availability of small unmanned aircraft systems and even simple drones allows investigation of stratigraphic architecture for geologists that were really at scales that were not attainable using conventional field geology methods. And incorporating the software or the technique of photogrammetry with the high-resolution images that result from this drone can create digital outcrop models that can be used for further interpretations and also can be very convenient teaching tools. And finally, pairing drone technology with readily available photogrammetry software really offers geoscientists a revolutionary and cost-effective methodology to investigate and quantify stratigraphic and structural questions that we might be asking in the field. And with that, I'll take any questions. Thank you very much.
Thank you. Are there any questions for Nora?
Yeah, John. What's involved in getting approval to fly?
So right now, this is changing. Originally, when I started flying this drone, especially in New Zealand, regulations were quite easy. So I just had to stay out of restricted airspace. Currently, even on Stanford's campus, I do have to go through the FAA to get regulation. And the reason they have that regulation currently is just they want to make sure that the person on the ground flying the thing always has eye contact with it. So as long as I agree to it, I can fly.